Okay, so in the last lecture we started exploring this question that if you have an extension of number field L over K and you take a prime in K, we want to find a algorithm to factorize it over L. We extend our P to L and we want to find the prime factorization of that, and to that end we proved a result about over local fields. What you do is you take L to be K alpha, you look at the minimal polynomial of alpha over K, and you consider that minimal polynomial as a polynomial in Kpx and you find its prime factorization there, and the factorization into irreducibles of that minimal polynomial will give you how many primes there are above P and how many and what the degree of the local fields would be. So, we can get more information by looking at residue fields and we will get to that today, but let me do an example first. So, let L let L be Q square root of 2. Okay. Let us say that P is equal to 7, and so we want to find prime factorization of 7 times OL, right. So, what we do is you take the minimal polynomial. So, minimal polynomial of square root of 2 over Q is x squared minus 2, right. So, you consider, so this is my phi x. So, you consider phi x in Q7x, and we know that x squared minus 2 factorizes as x minus alpha 1, x minus alpha 2 over Q7x. We proved that 2 has a square root in Q7, right, as an application of Hensel's lemma. We proved this. I mean, in fact, we saw this as an example even before we proved Hensel's lemma. Okay. Therefore, you should have 7 OL is P1 times P2 for P1 not equal to P2, right. So, in this case we kind of get pretty much complete information. Now, you take another case, let us say P is equal to 5. Okay. So, you consider phi of x in Q5 of x, and what happens here? Well, you can show, so maybe as this is an easy exercise, that phi of x is irreducible over Q5, right. What does that mean? This is a degree 2 polynomial. So, being irreducible is same as not having a root. So, you want to show that x squared minus 2 equal to 0 does not have a root in Q5, and you can show that by showing that if it has a root then it will be in Z5, which means that there will be a root in F5, okay. And we know that there is no root to x squared minus 2 congruent to 0 mod 5, okay. So, hence in this case 5 times OL is just P for a prime ideal P. Okay, that's not kind of quite true. It could have a power. So, it is either this or 5 OL is P squared. So, we do not know which case it is right now, right. So, that is why just looking at local fields does not give you complete information. In this case it could be P or it could be P square, we do not know, and this is the kind of things that we want to distinguish, and that is what we are going to do today. Okay. So, let me write a lemma now. So, L is let us say k alpha, right, and phi of x is minimal polynomial of alpha over k. So, now assume that alpha belongs to OL. We can always assume this by clearing the denominators. Okay. Further, suppose P does not divide the index of OK alpha in OL. So, this is an extra condition that I was talking about, right, and let P be a prime in OK above this rational prime P. Okay. All right. Now, so what I do is I consider the image of phi of x in k sub p of x, right. So, phi of x is contained in OKX and there is a map to k sub p of x. This is just OK mod p of x, right. And so, phi of x here goes to, I will call it phi bar of x. Then phi bar of x is product I going from 1 to r psi I of x to the power ei, where psi I of x is irreducible over kp of x, right, over, I mean in kp of x, maybe I will say in rather than over, that is more accurate. Okay. And psi I of x is not equal to psi j of x if I is not equal to j. Further, we can also say a little more about its degree. So, degree of psi I of x is equal to fi, right. So, here of course, ei's and fi's have this meaning that we had before. Here POL is P1 to the E1 up to PR to the ER, that is one thing. Moreover, what we have is the following. So, if gi of x in OKX is a lift of psi I of x, then Pi is simply the prime ideal generated by P, sorry, not this kind of P, but the script P and gi of x. Okay, so now we have pretty much complete, we have pretty much complete information. The only caveat is that the rational prime P should not divide this index. So, this could leave out finitely many primes from the list, right. We may not be able to do this for finitely many primes. Of course, we could try to change alpha and get some more information, but there is no guarantee that this will always work. You may always leave out a finite number of primes, but that is what we have to live with, and so we can try to use a different method for those primes. Okay. Now, how do we prove this? Well, we use the information that we have before, right. So, recall that phi of x is product I going from 1 to r phi I of x over k sub p of x, right, or in k sub p of x. So, what I do is I take you consider phi 1 of x, let us say, in k sub p of x, right. So, this is image of phi 1 of x in k p x, and we call it phi 1 bar, right. So, let beta in k p bar, this is algebraic closure, be a root of phi 1 bar of x. So, every element of k p beta is of the form summation, yeah, I don't know what to write it as, let us say C I bar beta to the I, right, and every element of O sub p 1 is of the form summation C I alpha to the I. Remember that as p does not divide O L O k alpha, we have P O 1 or P O I, any of them is equal to O sub p of alpha. So, this is where we are using that the index is co-prime to p, the index is co-prime to p, right. Hence, we have, so therefore, we have a surjective map, a surjection from O p 1 to k p, k small p of alpha, sorry, beta, confusing myself, beta, where alpha maps to beta, and this induces an isomorphism k p 1 to k p of beta. So, that is fantastic because we now have some relation between the two. So, therefore, degree of k p beta over k p is equal to f I, sorry, f 1, we are just working with 1 as a illustrative example, and then same thing works for everything else, k p 1 k p, okay. So, let g 1 of x in O k x be a lift of psi 1, then we have that p and g 1 of alpha is contained in p 1. I hope I wrote alpha there in this. Yeah, this statement I should, this makes no sense. I mean, x is a variable, I should have alpha here. Okay. All right. So, yeah, so this is contained in P 1 and I want to show that they are equal, right. So, this is another point where we use the co-primeness of what we have. So, any element in P 1 is of the form h of alpha for some h of x inside k x. So, here again we use that P does not divide O L O k alpha, right, this index. Okay, but this means that but this means that h of x minus g1 x h1 of x has, so this means that there exists h1 x such that this has coefficients in P, right, and modulo P, this g1 of alpha is 0, right. So, hence h of alpha belongs to P and g1 of alpha, right. Okay. So, that gives P g1 of alpha is equal to P1, right. We still need to show, we started with some prime factor of phi 1, right. We started with some irreducible factor of phi 1, we want to show that it is actually of the form that we are saying, right. Okay. So, what we do is we do this for all I between 1 and r, right. So, we want to show that phi 1 of x bar is psi 1 of x to some power c 1. Right. Okay. So, how do we show this, right? I mean, it could have different factors, but this does not happen over finite fields, right. So, what we can have is yeah, let me just think about this for a second. Yeah, okay. So, let's postpone the proof of this fact. So, let's assume the claim for now. Then degree of phi 1 bar, this is EI Fi, is equal to degree of psi 1 to the C1, which is this should be F1 times C1, right. Hence, E1 is equal to C1 and we get what we want. So, therefore, EI is equal to let me write it like this. So, therefore, phi bar of x is psi 1 of x to the E1 and so on up to psi r of x to the ER. Okay. So, all that remains is to prove the claim. So, go back to our example. Right. So, what do we have in this case? We have L is equal to Q square root of 2. Not only that, we have OL is equal to Z square root of 2, right. And so, the index of Z square root of 2 in OL is actually 1. So, we are not excluding any primes. So, again look at P equal to 7 and so you consider the minimal polynomial of this over Q7 or F7. So, x squared minus 2 is congruent to x minus 3 and x plus 3 mod 7. Okay. So, hence 7 OL is P1 times P2, and you consider P equal to P equal to 5. This gives x squared minus 2 is congruent to x squared minus 2 mod 5, right. So, this is irreducible over F5. Hence, now we couldn't distinguish whether 5OL was P or P squared, but now we know that it's P. So, E1 is equal to 1 and F1 is equal to 2 and R is 1. Right. You can also take P equal to 2 and we get x squared minus 2 is congruent to x squared mod 2. Right. So, we get 2 times OL is P squared, right. So, R is equal to 1, E is equal to 1, sorry, E is equal to 2 and F is equal to 1, right. Okay. So, that's an example, and we could do many more examples like this. So, let me do one more example of a cubic field, but we won't do a I'll state some fact. So, L is cube root of 2, right. So, minimal polynomial of this is x cubed minus 2, and here is a fact which I am pretty sure is true. OL is z cube root of 2. This is not entirely easy to prove, but one can prove this, and there is a lot of calculation involved, but let's assume this, and so OL z cube root of 2 is 1, right. So, now you can take some prime, let us say P equal to 7, and so you consider x cube minus 2 mod 7, and does it have a root? So, x to the, so this has no root, right. So, has no root modulo 7, right, because the only cubes modulo 7 are plus 1 and minus 1, right. X to the 6 is 1, and so the only roots are plus 1 and minus 1. So, there is no root. So, this is irreducible, hence x cube minus 2 is irreducible over F7, and so we get 7 OL is P, right. So, R is 1, E is 1 and F is equal to 3. Right. So, let us take P equal to 5, okay, and so there are 0, 1, 2, 3, 4, right, and 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, which is 3. So, this is mod 5. So, everything is mod 5. 3 cubed is 27, which is 2 mod 5, and 4 cubed is 64, which is 4 mod 5, right. So, everything is mod 5. Okay. So, x cubed minus 2 has a unique root in F5, okay, and it is not a multiple root. Therefore, x cubed minus 2 is x cubed minus x minus 3 times some quadratic polynomial, which I won't write, which I will not try to find, but here is an exercise, if you do not believe me, is that this is irreducible over F5. Okay. And so, if you take 5 OL, this will be P1 times P2. So, R is 2, E1 is 1, F1 is 1, E2 is 1 and F2 is 2. Right. So, 1 times 1 plus 1 times 2 is 3. So, you can do such things. Moreover, you will have P1 is 5 comma cube root of 2 minus 3 and P2 will be 5 comma cube root of 2 squared plus A times cube root of 2 plus B. So, you can find this A and B easily. I just did not bother to find it here. So, you can do you can practice other examples like this. Okay. So, today we looked at how to find prime factorization of a prime in the smaller number field if you extend it to the bigger number field. There is our result excludes finitely many primes, namely the primes which divide residue which divide the index of OK alpha in OL. Okay, but in practice this is not such a big restriction, although there are examples when you will have to exclude a finite set of primes no matter what alpha you choose. Okay. So, we will continue this study next time. Thank you.